Hello students. Uh, Let me discuss some model questions or say possible questions for the exam just to boost up your confidence because I'm getting messages from a lot of you worried what type of questions you'll get. So what I suggest is first you go through the respective hand notes and videos on this topic, and only after that you watch this video. Means you be accustomed or be thorough with what I had already circulated on these topics, and then you watch this video. So I am planning to do these videos as a series of 2 or 3 videos. So in this video I will exclusively discuss the topic of plate with holes, okay, or what are the different questions or question bank that is possible as part of this topic. Okay, so plate with hole, we have seen what it is all about. Now, see, basically, I can ask you any type of question, right? 1 mark question, 2 mark question, 3 mark question. So anything is possible, and you can also expect anything. So one of the questions I can ask you is, where is the Saint Venant's principle applied in the solution of plate with hole? So remember that, see, this is our original problem, okay, and this problem we are converting to this problem, okay. So that is possible by applying Saint Venant's principle. So Saint Venant, we have also seen it in torsion, and it appears at many places in advanced solid mechanics. So many of uh, the theories and formulations were taken from him. Now, what happens is, see, how Saint Venant's principle is applied is, see, the size of the hole is much lesser than the size of the plate. Okay, so stress concentration will be there, but what he is saying is that at distances very large from the hole, the effect of the hole will vanish, or in other words, the stresses at distances very large from the hole will be fairly uniform and will not have the effect of plate with hole. Now this particular principle is actually basically started from a different aspect, like, when you have a beam subjected to a point load, uh, at the locations close to point load you will have high stress, right? But at distances far away, uh, uh, you will have stresses which are uniform. Okay, anyway, I won't go into that principle deeply, but this much I will say, the effect of stress concentration due to hole will be negligible as you move to distances far away from the hole. That is also possible since the size of the hole is much lesser compared to width of the plane. Okay, so maybe I can ask Saint Venant's principle separately. How is it applicable for problem with plate with hole, as a 1 mark question, right? Or I can ask it couple with what is the relationship between width of plate and size of hole. So all these things, it is available, and now I can also ask you, see, in the problem we have solved, you have stresses along x direction. What if there is no stress along x direction and there is stress along y direction? So how will the derivation change? So what happens is, see, this is the equations that we use to convert between polar and Cartesian coordinates, right? So here, if you don't have stresses along x direction, and if you have stresses only along y direction, basically sigma x will be 0, and you will have sigma y as equal to the applied stress. So accordingly, these expressions will have small differences, and that will change the uh, derivation or the following derivation a little bit. Okay, so I may not ask the full derivation, but at least I can ask you 1 mark or 2 mark how it changes the course of derivation. Then we looked at this, so we said that applying Saint-Venant's principle, solving this problem is equal to solving this problem. Okay, so this particular problem we split it into two problems, right? Now, based on just this particular set of figures, there are numerous questions that can be asked. Okay, so remember, first of all, we are using the principle of superposition. So, as I discussed, if everything is in linear range, you can split the problem as sum of two different problems. Now we use this is very much used in advanced solid mechanics, even in structural analysis we use it every now and then without realizing it. So if you have a beam subject to UDL plus point load, so as long as the deflections and stresses are within linear range, the deflection due to point load plus deflection due to UDL will give deflection due to the total loads. So that is the principle of superposition that we are used here again. Now here one of the tricks that we are used in solving this is we have split the problem into two parts in such a way that one part has loads which are independent of theta, or loads which are basically symmetric about the axis. Okay, so based on this only we had used this particular formulations which we had seen it. I'm going to the Timoshenko textbook, so it is in page 59. Okay, so we had used this particular solution. Now I can ask you a trick question, like a circular plate is subjected to uniform load, uniform stress S by 2 at the ends. Okay, what will be the expression for stresses at different points? So the solution is nothing but everything that we have discussed here. Okay, so basically it is this formulation. So you have sigma, you know what is Pi and what is Po. These are the crucial things here. Okay, so maybe instead of external surface I can give you that the holes are subjected to a uniform pressure. I can give you whatever. So depending upon that, Pi internal pressure and Po outer pressure can change, which will change these expressions. So when you substitute those into these expressions, you will get the value expressions for sigma r and sigma theta. Okay, so that is one possibility. Okay, now another possibility is I can ask you based on this. Maybe I can ask you the exact same question. So a circular plate is subjected to uniform external sigma r load of S by 2 cos 2 theta and any uniform shear stress along the boundary of minus half S sin 2 theta. What is the solution for uh, the stress at any given point? So it is nothing but the entire derivation from this point that continues. So if I go to the next report, see, finally we had written this, right? The total stress is this plus this. So this is due to the symmetric portion, symmetric about axis portion. So if only this part is there, you will only have this portion. Okay, so in which case total stress will have only this component and not this component. Okay, so just it's actually it's simple only, it's not way too complicated. So just be cautious of that. Now I can again ask, see, um, in this particular a circular plate is subjected to following load. So I can give you a case where there is no shear stress and only this normal stress, or I can give you only the shear stress and non normal stress. All those things are possible. So how will the derivation change if I do that? Well, see, if you look at the solution, basically what changes is the boundary condition that we are applying. See, we have four constants for which we will use four boundary conditions. So if the external stresses change, you have a change in boundary condition which will change the solution. Now, of course, this is a 4 by 4 matrix. I am not expecting you to solve this, but questions will be asked accordingly, such that you won't be able to you are not needed to solve this. Okay, you might be required to just write the formulations or the steps or whatever. Okay, so these are some of the possibilities I can ask from this page. Okay, now I can also ask direct numerical questions. I can suppose, if in this case I can ask you, I can give you the values of S, A, B and things like that, and evaluate the stresses at these points. Those questions can be asked. And yeah, it will be nothing but simple substitution. Now I can also ask, see, based on this derivation, okay, in this derivation, what is this? This is nothing but the compatibility condition that needs to be satisfied in polar coordinates. So I can ask you maybe a 1 mark question. What is the compatibility condition in polar coordinates? Okay, so this is the equation that we had seen much before. Yeah, this one, right? Okay, so that is that. Now these are all steps which, of course, I can't ask the exact same derivation, right? Because it will be just copying from the book. But just know what's going on, and if I ask you some changes, for example in boundary conditions, you should be able to apply your mind. That's all, and don't worry about solving this. Okay, so this is, now let us come to this total stresses. So these are the expression for total stresses for the original problem, right? This is a problem. Now I can ask you direct numerical. I can give you S A by R theta location on the plate, and I can ask you to evaluate any of these stresses. Or I can do one thing, I can give you the ratio of sigma theta and tau r theta, or ratio of any two stresses. I can give you theta, and I can ask you to evaluate which is the A by R, or which is the location that we are trying to evaluate. So those things can be asked. So if I am giving you the ratio and theta, using theta you can first simplify the expression, and then when you take the ratio of any two stresses, you can see that S is cancelling, the external stress is cancelling, so you don't need that. Then it will be like a equation in fourth power of A by R, right? So maybe what you can do is A square by R square, and A raised to 4 by R raised to 4 is coming everywhere, right? So A square by R square, you can give it as some X. Okay, so if you give A square by R square as X, A raised to 4 by R raised to 4 will be X square. So it will be essentially like a quadratic equation, and you will be able to solve it. Okay, so that is another category of problems I can ask you. And then coming to this, so this was all about the interpretation, right? So you have the final expressions for stresses, which are these. So we started out by with the boundary condition. So to check back the formula, if you give as r tends to infinity, you should be able to get the initial values. So I can ask you some indirect questions based on this, indirect or direct, maybe 1 mark, maybe 2 mark, whatever. So those are some questions. Now yeah, so stress concentration, I can also ask you, what do you mean by stress concentration? So here you can see sigma theta is 3 times the external applied stress. Okay, so external applied stress is S. Okay, so generally you expect the same stress, but due to the hold, effect of hold, here the sigma theta is 3 times the stress and it reduces, right? So this is the stress diagram. So I can ask you some direct or indirect questions based on that, either theory questions, what do you mean by stress concentration for a plate where hold size is very less and you have applied stress along x direction, how much is the stress concentration? It is 3 times. So those things can be asked, which are nothing but the interpretation of these formulas. Okay, uh, and there are some other things also. If you substitute certain values, you'll get those values. So sigma theta at theta equal to 0 or theta equal to pi is basically this location, this location. You will have a compression, okay, equal compressive stress. So I can ask you something based on that also. And yeah, it is, that is basically it. And I can ask you what is the some theory behind the application of stress concentration, or the applications of these formulas where we have weight with the hold. And suppose if I ask you this question, so you have two applied stresses on two direction, right? So you can do like a principle of superposition. Of course I may not ask the full derivation because it's like exhaustive, but maybe I can ask you for 1 or 2 marks, how will you solve this problem? Now you know the solution of this problem. Okay, so you can solve it as sum of this plus another plate with stresses along y direction. Okay, so again it is using principle of superposition. And yeah, so just know the thing how its derivation proceed, that's all. So this is it, and hope this video brings you more comfort than misery. Okay, so if you have any doubts, let me know. Thank you.